10% of our planet's surface lies buried beneath ice, a frozen archive stretching back hundreds of thousands of years, holding within it the breath of ancient atmospheres, the dust of forgotten volcanoes, and the stillness of ages no human ever witnessed. If all of this ice were to melt, the oceans would rise by nearly 70 meters, swallowing coastlines and redrawing the map of every continent. And yet this vast white expanse remains one of the least understood realms on Earth, a world of silence and slow motion where time itself seems to freeze. Tonight, we journey into the frozen places of our planet, the glaciers that carve mountains, the ice sheets that hold the memory of Earth's climate, and the permafrost that preserves secrets older than civilization. This is glaciology made peaceful, the science of ice transformed into a lullaby for the curious mind. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will drift toward you like snowflakes settling on a still landscape. There is nothing to memorize, nothing to remember. Just listen and let your mind wander into the cold, quiet beauty of Earth's frozen places. Have you ever wondered what stories lie trapped within a glacier, or why ice that fell as snow 1,000,000 years ago still exists today? You are not alone. If these frozen truths bring you peace, consider leaving a like and subscribing to join our community of restful learners. Let your breathing slow, like the patient movement of a glacier. Feel the weight of your body sinking into softness and allow the stillness to gather around you like fresh snow. The frozen world is patient. It has waited millennia for you to listen. Let us begin. Glaciers are rivers of ice that flow so slowly they seem frozen in time. A glacier does not rush. It moves with a patience measured in centuries, advancing perhaps a few centimeters each day, carving valleys and reshaping mountains with a force that defies its stillness. These rivers of compressed snow begin high in the mountains or in polar regions, where more snow falls each year than can melt, building layer upon layer until the weight transforms flakes into dense ice. Under immense pressure, this ice begins to flow, not like water racing downhill, but like thick honey spreading across a tilted surface, so slowly that a human lifetime might witness only a fraction of its journey. Glaciers carry boulders the size of houses, grind bedrock into fine powder, and leave behind landscapes that bear their signature for millennia. Across the cold places of Earth, glaciers are creeping forward and backward, breathing with the seasons. They are the patient sculptors of our world. Ice becomes a glacier only when it grows thick enough to move under its own weight. Snow that falls on a glacier does not simply pile up and wait. Over years and decades, the weight of new snow compresses the layers beneath, squeezing out the air and transforming delicate flakes into dense granular ice called firn. With continued accumulation, firn becomes glacial ice, a substance so compact that it behaves more like a very slow liquid than a solid. Once the ice reaches a thickness of roughly 30 to 60 meters, the pressure becomes so immense that the ice at the bottom begins to deform and flow, even on slopes so gentle they would barely trouble a rolling ball. This threshold marks the birth of a glacier, the moment when a static mass of frozen water awakens into motion. The transformation takes decades or even centuries, a process invisible to the hurried eye but as inevitable as the turning of the seasons. What begins as a single snowflake eventually joins a river of ice. The ice in a glacier can be thousands of years old, preserving snow that fell before recorded history. Deep within a glacier, the ice you would touch today may have formed from snow that fell when ancient civilizations were first building their cities. Each layer represents a moment in time, a winter long forgotten, preserved in crystalline form as pages in a book. As new snow accumulates on the surface, older layers are pushed deeper, compressing under the growing weight above. In the great ice sheets of Antarctica and Greenland, ice near the bottom has been there for hundreds of thousands of years, holding tiny bubbles of air that were sealed away before humans existed. The glacier becomes an archive of Earth's atmosphere, a frozen library where each chapter was written by falling snow. When scientists drill into these ancient layers, they are reaching back through time, touching winters that no human ever witnessed and reconstructing climates that shaped life itself. Glacial ice appears blue because it absorbs red light and reflects blue wavelengths back to our eyes. The blue glow of ancient glacial ice is not a trick of the light, but a consequence of physics and time. When sunlight enters ice, it passes through layers so dense that ordinary scattering cannot occur as it does in snow. The longer wavelengths of red and yellow light are absorbed by the ice, their energy swallowed by the crystalline structure, while the shorter wavelengths of blue scatter back to the observer. The deeper the ice, the more intense this blue becomes, as centuries of compression have squeezed out nearly all the air bubbles that would otherwise scatter light in every direction. Standing before a glacial crevasse, one might see shades of blue so vivid they seem almost luminous, as though lit from within. This color is the signature of time itself, visible proof that light is traveling through ice formed over thousands of years. Antarctica holds roughly 70% of all the fresh water on Earth, locked within its ice sheets. Beneath the endless white of Antarctica lies a reservoir of fresh water so vast that it defies imagination. If you could gather all the rivers, lakes, and groundwater on every continent combined, it would still not match the volume of frozen water held in the Antarctic ice sheets. This ice, averaging over 2 kilometers thick across the continent, represents millions of years of accumulated snowfall, each flake adding to a treasury of pure water isolated from the rest of the world. The ice is so heavy that it has pressed the underlying land below sea level, and so extensive that it reflects enough sunlight to influence global temperatures. Every drop of this frozen water began as a snowflake drifting through polar skies, landing on a landscape where it would remain for millennia. Antarctica is not merely a frozen desert. It is the greatest store of fresh water our planet possesses. The oldest ice ever found on Earth is nearly 3 million years old. In the cold depths of Antarctic ice cores, scientists have discovered ice that formed when our distant ancestors were still learning to walk upright on the African savanna. This ancient ice, extracted from locations where accumulation rates are exceptionally low and temperatures have remained stable, contains tiny bubbles of air sealed away before the first humans existed. Analyzing these bubbles reveals the composition of Earth's atmosphere across vast stretches of time, allowing researchers to trace how carbon dioxide and methane levels have fluctuated through ice ages and warm periods. The search for ever older ice continues, with expeditions drilling into remote regions of Antarctica hoping to find samples stretching back even further. This ancient ice is fragile, irreplaceable, and precious. It holds the breath of an Earth we will never otherwise know. And from the ancient origins of ice itself, we now turn to the great frozen cycles that have shaped our planet. Earth has experienced at least 5 major ice ages over the past 3 billion years. Our planet has not always been the temperate world we know today. Throughout its history, Earth has repeatedly plunged into periods of extreme cold, when ice sheets spread far beyond the poles to cover vast swathes of the continents. These ice ages, each lasting millions of years, have come and gone with a rhythm tied to the drift of continents, the composition of the atmosphere, and variations in Earth's orbit around the Sun. Between these great freezings, the planet has basked in warmer climates where palm trees grew near the poles and crocodiles swam in Arctic waters. The ice ages have shaped the evolution of life, forcing species to adapt, migrate, or perish, and they have carved the landscapes we inhabit today. We live in a world bearing the scars of these frozen eras. The story of ice is woven into every valley, every lake, every mountain shaped by glaciers. During the last ice age, glaciers covered nearly 30% of Earth's land surface. 20,000 years ago, the world looked profoundly different. Massive ice sheets, kilometers thick, blanketed much of North America, reaching as far south as present-day New York, while similar glaciers covered Scandinavia and reached deep into Europe. The British Isles were joined to mainland Europe by dry land, and sea levels stood over 100 meters lower than today, exposing vast coastal plains now submerged. Mammoths and woolly rhinoceroses roamed the frozen steppes, and early humans huddled in caves, painting images of the animals they hunted by firelight. The weight of the ice was so immense that it pressed the land downward, and even now, thousands of years after the glaciers retreated, Scandinavia continues to slowly rise as the Earth recovers from that burden. The last ice age was not a distant event. It was the world your ancestors knew. The current ice age began about 2.5 million years ago and continues to this day. We are living within an ice age, though we rarely think of it that way. The Quaternary glaciation, as scientists call it, began roughly 2.5 million years ago when ice first started to accumulate on Greenland, and Antarctica began to expand its frozen grip. Since then, glaciers have advanced and retreated in cycles, driven by subtle shifts in Earth's orbit that alter how much sunlight reaches the poles. We happen to be living in a warmer interval within this larger ice age, a period called an interglacial, when the ice has pulled back to the polar regions and left most of the continents free. But the ice has not gone away. It waits in Antarctica and Greenland, in mountain glaciers scattered across every continent, a constant reminder that our warm, green world is merely a pause in a much longer story of cold. The Ice Age is not history, it is still ongoing. Ice ages are punctuated by warmer periods called interglacials, and we are living in one now. Within every great ice age, there are rhythms of advance and retreat, times when glaciers surge across continents and times when they withdraw to the highest mountains and coldest poles. These warmer intervals, called interglacials, typically last between 10 and 30,000 years, and during them the ice recedes, forests spread northward, sea levels rise, and life flourishes in regions recently buried under frozen weight. The current interglacial, known as the Holocene, began roughly 12,000 years ago, and within its warmth, human civilization arose, developed agriculture, built cities, and began to reshape the planet. We live in a brief window of relative warmth, a pause between glacial advances that have defined the last several million years. There is something humbling in knowing that everything we have built exists within a fleeting thaw. The ice waits patiently. Milankovitch cycles, the slow wobbles and tilts of Earth's orbit, help trigger the rhythm of ice ages. The ice ages do not arrive at random. They follow a rhythm set by the geometry of Earth's journey around the Sun, cycles first described by a Serbian mathematician named Milutin Milankovitch in the early 20th century. Over tens of thousands of years, the tilt of Earth's axis shifts, the shape of its orbit stretches and contracts, and the timing of its closest approach to the Sun drifts through the calendar. These subtle variations change how much sunlight reaches the polar regions in summer, and when summers grow cool enough that snow survives year after year, glaciers begin their slow expansion. The cycles repeat with a regularity that can be read in ancient ice and ocean sediments, a clockwork of cold written into the motion of our planet through space. The ice ages are not accidents. They are inevitable chapters told by the heavens. The most extreme ice age, called Snowball Earth, may have frozen the entire planet over 700 million years ago. In the deep past, before complex animals crawled from the primordial seas, Earth may have frozen entirely, its vast oceans locked beneath thick ice from pole to equator. This snowball Earth, as scientists call it, would have been a world of profound white silence, where even the tropics lay buried beneath glaciers, and the only open water existed near volcanic hotspots or narrow leads in the ice. How life survived this extreme freeze remains a subject of deep inquiry, yet survive it did, perhaps clinging to warmth near deep-sea vents or in pockets of liquid water beneath the frozen surface. When the ice finally retreated, it left behind strange geological signatures that can still be read today. Snowball Earth reminds us that our planet's climate can shift to extremes almost unimaginable from our vantage. And from the deep past of global freezing, we now venture to the coldest continent on Earth. Antarctica is the driest, windiest, and coldest continent, a desert of ice beneath endless twilight. Antarctica holds more extremes than any other place on Earth. It receives so little precipitation that much of its interior qualifies as a polar desert, yet it is covered in ice kilometers thick because the snow that falls almost never melts. Winds sweep across its high plateau with a fury unmatched anywhere else on the entire planet, katabatic gusts that pour down from the interior toward the coast, sometimes reaching speeds that would flatten a standing person. The temperatures plunge lower than anywhere else on the planet, cold enough to freeze exposed skin in moments and to make metal brittle as glass. In winter, the continent lies in months of complete darkness, and in summer, the sun circles the horizon without ever setting. Antarctica is a place where human survival requires constant vigilance and effort. It is Earth's last great wilderness. The Antarctic ice sheet is so heavy that it has pushed the bedrock beneath it below sea level. The weight of the Antarctic ice sheet is almost beyond human comprehension. Many kilometers of densely packed frozen water press down upon the ancient continent with such relentless force that the land beneath has been deformed, pushed downward into the mantle like a heavy object sinking slowly into a soft mattress. If the ice were to vanish instantly, parts of Antarctica would lie far below the surface of the sea, though over thousands of years the land would slowly rise again, rebounding from its frozen burden in a process called isostatic adjustment. This depression reveals the immense scale of the ice that covers the entire continent, a mass so great it warps the very crust of the Earth. The weight pressing down is not merely sitting upon the rock. It is reshaping the planet itself, sculpting it slowly over millions of years. Some Antarctic ice is nearly 5 kilometers thick, taller than any mountain in the Alps. In the heart of East Antarctica, the ice reaches depths that are almost impossible to visualize. If you could somehow stand at the very base of this immense frozen mass and look upward, you would be gazing through nearly 5 kilometers of ice, a distance greater than the height of Mont Blanc or any summit in the Alps. This ice accumulated snowflake by snowflake over millions of years, each layer compressing those beneath it, until the deepest ice has been squeezed into a dense, crystalline form unlike anything found on the surface. Drilling into this ice is like drilling into time itself, each meter representing centuries of frozen history, each bubble of trapped air a sample of an ancient atmosphere. The sheer thickness of the Antarctic ice sheet is a reminder of how patient the cold can be, building its empire one winter at a time. And as you rest with these frozen truths, let them settle over you like a blanket of fresh snow. There is no need to hold onto any of them. Let your breath slow, let your body soften, and allow the stillness to deepen. Lake Vostok lies hidden beneath 4 kilometers of Antarctic ice, isolated for millions of years. Buried beneath the vast ice sheet of East Antarctica lies a lake larger than any in Western Europe, a body of liquid water that has been sealed away from the outside world for perhaps 15 million years. Lake Vostok, named after the Russian research station that sits on the ice above it, exists in total darkness, kept liquid by geothermal heat from below and insulated by the kilometers of ice pressing down from above. Scientists believe this hidden lake may harbor life, organisms that have evolved in complete isolation from the rest of the biosphere over unimaginable spans of time. Efforts to drill down and sample its waters have been undertaken with care to avoid contaminating this pristine environment. Vostok is not merely a curiosity. It is a window into how life might persist in frozen oceans beneath the icy moons of our solar system. The coldest temperature ever recorded on Earth was -89.2 degrees Celsius in Antarctica. On a winter night in 1983, instruments at the Soviet Vostok station recorded a temperature that even seasoned polar researchers found difficult to comprehend. At -89.2 degrees Celsius, the air itself becomes a mortal danger, freezing exposed skin in seconds and turning ordinary materials brittle enough to shatter. At such temperatures, boiling water thrown into the air turns instantly to ice crystals before it can reach the ground, a demonstration of how hostile this environment truly is. The interior of Antarctica, far from any moderating ocean influence, routinely experiences conditions more extreme than anywhere else on the planet. Satellite measurements have since detected even colder temperatures in isolated pockets, though these remain unofficial records. This is a realm where the cold is not merely uncomfortable, it is absolute. Antarctica was once a warm, forested continent before it drifted to the South Pole and froze. Beneath the ice of Antarctica lie the fossils of a very different world. Millions of years ago, before the continent drifted to its present position at the bottom of the Earth, Antarctica was warm, green, and teeming with life. Forests of southern beech and ancient conifers covered its rolling hills, and dinosaurs roamed valleys that have since been buried under kilometers of ice. Fossil evidence shows that this land once knew seasons of growth and abundance, a climate more like that of present-day New Zealand than the frozen desert it has become. As the continent slowly shifted and Antarctica settled over the South Pole, circumpolar currents isolated it from warmer waters, and the ice began its relentless conquest. The forests vanished, the dinosaurs disappeared, and the land became a blank white page. The memory of that warmer world waits beneath the ice. And from the frozen south, we now travel to the opposite end of the Earth, where ice floats upon dark Arctic waters. The Arctic is an ocean surrounded by continents, while Antarctica is a continent surrounded by ocean. The two polar regions of Earth are mirror opposites in more ways than their extreme temperatures alone. The Arctic is fundamentally an ocean basin, its ice floating upon dark, frigid waters encircled by the northern coasts of North America, Europe, and Asia. Antarctica, by contrast, is a vast landmass buried under ice, an entire continent sitting at the bottom of the world, with the southern ocean surrounding it on all sides. This fundamental difference shapes everything about how these regions behave, from the way sea ice forms and melts to the creatures that call each place home. Polar bears hunt seals on Arctic sea ice, while penguins waddle across Antarctic shores that no bear has ever seen. The poles are not the same. They are two profoundly different frozen worlds, each unique in character and shaped by their particular geography. Arctic sea ice forms from frozen seawater and can be distinguished from glacial ice by its saltiness. When seawater freezes, it does not become pure ice. The salt is slowly pushed out as the ice crystals form, creating brine channels that snake through the frozen mass and eventually drain back into the ocean below. Fresh sea ice retains some of this salt, giving it a different character from the glacier ice that breaks off from land-based ice sheets and drifts as icebergs. As sea ice ages and survives multiple summers, more salt drains away, and the ice becomes fresher, harder, and more translucent. Experienced polar travelers can distinguish old multi-year ice from younger seasonal ice by its color and texture alone. The difference matters for navigation, for wildlife habitat, and for understanding how the climate is changing. The Arctic Ocean's ice is not just frozen water. It is frozen seawater, a product of an entirely different process than the glaciers that flow from the land. The Greenland ice sheet contains enough water to raise global sea levels by over 7 meters. The Greenland ice sheet is the second largest mass of ice on Earth, smaller only than Antarctica, but still vast beyond easy comprehension. If every gram of this frozen water were to melt and flow into the oceans, sea levels around the world would rise by more than 7 meters, enough to flood countless coastal cities from New York to Shanghai, from London to Mumbai and beyond. The ice sheet covers most of the island, reaching several kilometers thick in places, pressing down on ancient rock that has not seen sunlight for millions of years. This ice is not static. Rivers of meltwater flow across its surface in summer, plunging into deep holes called moulins that carry water down to the bedrock below. The Greenland ice sheet is a frozen reservoir of enormous power. Its future is intertwined with the future of coastlines everywhere. Icebergs calve from glaciers with thunderous cracks that can be heard kilometers away. When a glacier meets the sea, pieces of ice break away in a dramatic process called calving, and the sound is unlike anything else in nature. Deep groans and sharp cracks echo across the water as chunks of ice, sometimes as large as entire city blocks, separate from the glacier face and crash into the ocean below, sending spray high into the cold air. The splash sends waves rolling outward, and the newly born iceberg bobs and rolls as it finds its balance in the water. These icebergs carry within them the compressed snow of many centuries, ancient ice that has traveled slowly from the interior of ice sheets to the coast. Some drift for years through polar seas, gradually melting and releasing fresh water back into the ocean. The birth of an iceberg is a dramatic moment in the patient life of a glacier, a thunderous release of frozen time. The Arctic Ocean's ice cover has been shrinking dramatically over the past few decades. Satellite images reveal a transformation that is reshaping the very top of the world. The Arctic Ocean's summer ice extent has declined significantly since satellite records began in the late 20th century, and the ice that remains is thinner and younger than it once was. Where thick multi-year ice once dominated, now much of the Arctic is covered by seasonal ice that forms in winter and melts by summer's end. The shrinking ice opens new shipping routes, exposes new resources, and changes the habitat for every creature that depends on the frozen ocean. The loss of reflective white ice means more sunlight is absorbed by the dark ocean waters, warming them further in a feedback loop that accelerates the change. The Arctic is changing faster than almost any other place on Earth. What once seemed permanent is revealing itself to be fragile. Polar bears depend entirely on sea ice as their hunting platform, drifting with the frozen ocean. The polar bear is a creature of the ice, perfectly adapted to a life spent roaming freely on the frozen sea. These powerful and patient white animals traverse the vast Arctic ice, hunting ringed seals at breathing holes and along the edges of leads where open water meets the frozen surface. Without sea ice, polar bears cannot reach their primary prey, and as the ice retreats earlier in spring and returns later in autumn, the bears face ever longer fasting periods on land. Some bears now swim vast distances between the ice flows, expending energy they can ill afford to lose. The relationship between polar bear and sea ice is intimate and ancient, forged over hundreds of thousands of years of patient evolution. As the ice changes, so too must the bear. The future of this iconic predator is written in the shifting patterns of Arctic ice. And from the drifting ice of the Arctic seas, we now descend into the frozen ground beneath the surface. Permafrost is ground that remains frozen for at least 2 consecutive years, though most is far older. Deep beneath the surface of the Arctic and subarctic regions lies a hidden world of frozen soil, rock, and sediment that has remained solid for centuries, millennia, or even millions of years. This permafrost forms wherever the ground temperature stays below freezing year after year, trapping water as ice within the soil and binding the landscape together in a frozen grip. Above the permafrost, a thin, shallow, active layer thaws each summer, allowing plants to grow and animals to burrow, but beneath it, the ground remains locked in permanent ice. Permafrost can extend hundreds of meters deep, a subterranean realm of frozen earth that underlies entire vast expansive regions of the north. This frozen foundation supports buildings, roads, and pipelines. It is also a vault, preserving precious organic material from ages past. Nearly a quarter of the northern hemisphere's land surface is underlain by permafrost. Permafrost is far more widespread than many people realize. It underlies vast territories across Siberia, Alaska, Canada, and northern Europe, covering an area larger than the entire continent of Africa. In some places, the permafrost is continuous, a solid frozen layer beneath every square meter of ground stretching for thousands of kilometers. In others, it exists in patches, scattered through landscapes where conditions are just cold enough to preserve it. The presence of permafrost shapes everything about these northern lands, from the types of vegetation that can grow to the way rivers flow and lakes form. Communities across the Arctic have built their lives upon this frozen foundation, and the infrastructure of entire regions depends on the ground remaining stable. Permafrost is not just cold soil, it is the skeleton of the northern world. Some permafrost in Siberia has remained frozen for over 3 million years. In the coldest and most remote isolated regions of Siberia, the permafrost reaches back through time to an era when the world was profoundly different from today. This ancient frozen ground has remained solid through countless glacial and interglacial cycles, preserving within it a record of environments and ecosystems that have long since vanished from the surface of the Earth. Scientists drilling into these depths have found organic material, ancient plant roots, and microbes that have been locked in ice since before humans walked the African plains. The stability of this deep permafrost speaks to the constancy of the cold that has gripped these regions for millions of years. Yet even this ancient ice is now showing signs of warming at depths that were once thought impervious to change. The patience of the permafrost may finally be meeting its limit. Permafrost acts as a giant freezer, preserving ancient organic matter, bacteria, and even viruses. The frozen ground of the Arctic is a natural time capsule, preserving organic material in a state of suspended animation that would be entirely impossible in warmer soils. Plant matter, animal remains, and microorganisms that fell into this frozen earth thousands or millions of years ago remain remarkably intact, their cellular structures held in place by ice. Scientists have revived ancient bacteria from permafrost samples, organisms that have been dormant since before the pyramids were built. Viruses too have been found within the ice, some still capable of infecting hosts after tens of thousands of years in frozen storage. The permafrost does not merely store these relics, it keeps them in a state of preservation so complete that they can sometimes be brought back to life. The frozen ground is a museum of the ancient world. The remains of woolly mammoths found in permafrost are so well preserved that their flesh still exists. In the frozen ground of Siberia, hunters and scientists have discovered the remains of woolly mammoths so remarkably preserved that they seem to have died only recently, even though these ancient creatures perished tens of thousands of years ago. The unrelenting cold has kept their skin, muscle, and even blood in a state that defies the usual processes of decay. Some mammoth specimens have been found with food still in their stomachs, their last meals identifiable after millennia. The preservation is so complete that scientists have extracted intact DNA, fueling dreams of one day bringing these giants back through genetic technology. Each mammoth discovered is a window into the Ice Age, a direct physical connection to a world of grasslands, glaciers, and enormous beasts. The permafrost has guarded these bodies with care. As permafrost thaws, it releases methane, a greenhouse gas far more potent than carbon dioxide. Locked within the permafrost are vast quantities of organic carbon, the remains of plants and animals that accumulated over thousands of years when the ground was too cold for decomposition. As temperatures rise and permafrost begins to thaw, this ancient organic matter is exposed to microbes that break it down, releasing carbon dioxide and methane into the atmosphere. Methane is particularly concerning because it traps heat far more effectively than carbon dioxide, amplifying the warming that caused the thaw in the first place. In some cases, methane bubbles up from thawing lakes in quantities large enough to be set alight. Scientists watch these changes with concern, knowing that the permafrost holds more carbon than currently exists in the atmosphere. The thaw of permafrost may accelerate warming in ways still hard to predict. And from the frozen ground, we now turn to what lies within the ice itself, the time capsules of Earth's atmosphere. Air bubbles trapped in glacial ice contain samples of ancient atmospheres up to 800,000 years old. When snow falls upon a glacier and is slowly buried by more snow above, tiny pockets of air become trapped within the compressing layers. Over time, these bubbles are sealed within the ice, preserving perfect samples of the atmosphere as it existed on the day the snow fell. Scientists drilling deep into the ice sheets of Antarctica and Greenland have retrieved air that was breathed by no human, captured in an age before our species even existed. By analyzing the gases within these bubbles, researchers can measure the concentration of carbon dioxide, methane, and other trace gases throughout Earth's recent geological past. These measurements have revealed the natural rhythms of glacial and interglacial cycles, and they have shown how dramatically the composition of our atmosphere has changed. Each bubble is a message from the past, a breath of ancient air. Ice cores drilled from glaciers are like libraries of Earth's climate history. To read the history of our planet's climate, scientists venture to the most remote and frozen places on Earth, where they drill long cylinders of ice from glaciers and ice sheets. These ice cores, some stretching more than 3 kilometers deep, contain layer upon layer of compressed snow, each stratum representing a single year of accumulation. By examining the physical and chemical properties of each layer, researchers can reconstruct temperatures, precipitation patterns, volcanic activity, and atmospheric composition stretching back hundreds of thousands of years. The ice cores from Antarctica and Greenland have become among the most valuable archives in all of climate science, providing unbroken records of Earth's environmental history. Each core is a vertical timeline, a frozen chronicle of the planet's past. The deeper you drill, the further back in time you travel. Scientists can count annual layers in ice cores like tree rings to date past events. Just as the rings of a tree reveal the years of its growth, the layers within an ice core mark the passage of time in the frozen world. Each year's snowfall leaves a distinct band, visible as subtle variations in density, crystal structure, and chemical composition. In regions with strong seasonal contrast, summer layers may appear slightly different from winter layers, allowing researchers to count backwards through time with remarkable precision. By matching distinctive features, such as volcanic ash layers or sudden chemical changes, Across multiple ice cores from different locations, scientists can synchronize their chronologies and build a master timeline of Earth's recent past. This layer counting has allowed researchers to date events with accuracy measured in just a few years, even for ice that fell tens of thousands of years ago. It is slow and painstaking work. Volcanic eruptions leave distinct ash layers in ice that help mark specific years in history. When a great volcano erupts, it sends plumes of ash and sulfuric acid high into the atmosphere, where winds carry them around the globe and deposit them upon the ice sheets of the polar regions. These particles settle onto the snow and become preserved within the growing ice, creating a distinct layer that can be identified thousands of years later. By matching the chemical signature of volcanic ash in ice cores to known eruptions, scientists can pinpoint exact years in the ice record, providing anchor points for their chronologies. The eruption of Tambora in 1815, the Great Explosion of Krakatoa in 1883, and countless older eruptions have all left their marks in the ice. These volcanic layers serve as timestamps in the frozen archive. They are the punctuation marks of our planet's geological history. The ratio of oxygen isotopes in ice reveals the temperature of the atmosphere when the snow fell. Water molecules contain different isotopes of oxygen, some heavier than others, and the ratio between these isotopes changes with temperature. When the atmosphere is warmer, more of the heavier isotope makes it into precipitation, while colder conditions favor the lighter form. By measuring the oxygen isotope ratio in each layer of an ice core, scientists can reconstruct the temperature of the air when that snow originally fell. This powerful technique has allowed researchers to carefully track the rise and fall of global temperatures through ice ages and warm periods, revealing the natural rhythms of Earth's climate over hundreds of thousands of years. The precision of this method is remarkable, able to detect subtle changes of just a degree or two in ancient atmospheric temperatures. Each layer tells its own quiet thermal story. Ancient pollen and dust particles preserved in ice tell stories of distant ecosystems. The ice sheets of Antarctica and Greenland lie far from forests and grasslands, yet within their frozen layers, tiny grains of pollen, spores, and dust from faraway lands have been preserved. These particles travel enormous distances on the wind, carried aloft from continents thousands of kilometers away before settling gently upon the polar snows. By analyzing these microscopic travelers, scientists can learn about the ecosystems that produce them, tracking changes in vegetation and climate across entire regions of the Earth. Increases in dust often indicate drier, windier conditions on distant continents, while shifts in pollen types reveal the advance and retreat of forests. Each grain is a tiny messenger from a faraway world, a witness to conditions in lands the ice itself has never seen. The frozen archive connects the poles to the entire planet. And from the records preserved within ice, we now explore the living things that survive in frozen worlds. Extremophiles are organisms that thrive in conditions once thought impossible for life, including deep within glaciers. For many years, scientists believed that the frozen interior of a glacier was a sterile, lifeless place, too cold and too devoid of nutrients to support any living thing. Yet discoveries in recent decades have revealed a hidden world of extremophiles, organisms adapted to survive and even flourish in the harshest conditions imaginable. Deep within the ice, bacteria and other microorganisms have been found living in tiny veins of liquid water that persist even at temperatures well below freezing. These creatures have evolved remarkable adaptations to survive. Antifreeze proteins that prevent ice crystals from forming within their cells, and metabolism slowed to almost imperceptible rates. The discovery of life within glaciers has expanded our understanding of where life can exist. It has also raised questions about the possibility of life on icy moons far beyond Earth. Ice worms live their entire lives within the crystalline structure of glaciers. On the glaciers of the Pacific Northwest of North America and in other mountainous regions, peculiar black worms emerge from the ice at dawn and dusk to feed on algae and pollen on the glacier surface. These ice worms, each just a few centimeters long, spend their entire lives in and on glacial ice, an environment that would kill most other invertebrates within minutes. Their bodies contain special proteins that prevent ice crystals from forming in their tissues, allowing them to remain active and flexible at temperatures that would freeze other creatures solid. If exposed to warmth above just a few degrees, ice worms quickly die, their fragile bodies literally melting as their adapted proteins break down. These delicate creatures are a quiet reminder that life can specialize to fill almost any niche. The glacier is their only possible world. Cryoconite holes are miniature ecosystems on glacier surfaces, home to bacteria, algae, and tiny invertebrates. On the surface of glaciers around the world, dark dust particles absorb sunlight and slowly melt into the ice, creating small cylindrical holes that fill with meltwater. These cryoconite holes, typically just a few centimeters wide and deep, become miniature ecosystems, harboring communities of bacteria, algae, fungi, and tiny animals such as tardigrades and rotifers. The dark sediment at the bottom of each hole provides nutrients and a substrate for life, while the water offers protection from the extreme cold and drying winds above. Scientists have found that cryoconite holes can be remarkably productive, their tiny inhabitants cycling nutrients and fixing carbon at rates that rival more temperate ecosystems. Each hole is a self-contained world, a pocket of biological activity on an otherwise sterile expanse of ice. Some microbes in Antarctic ice can survive for hundreds of thousands of years in a dormant state. In the ancient ice of Antarctica, scientists have discovered microorganisms that have remained frozen and dormant for periods stretching back hundreds of thousands of years. When carefully thawed under sterile conditions, some of these ancient cells have revived, resuming metabolic activity as though they had been asleep for mere moments rather than millennia. These remarkable survivors have developed mechanisms to protect their DNA from the damage that accumulates over such vast timescales, and to repair any damage that does occur upon awakening. The ability of these microbes to endure such prolonged dormancy challenges our understanding of the limits of life and the meaning of survival itself. They are not merely preserved. They are patient, waiting in the ice for conditions to change. The cold has become their refuge, not their prison. Let these quiet wonders of frozen life settle gently into your thoughts. There is no need to remember any of it. Allow your muscles to release, your breath to slow, and let the stillness wrap around you like the silence of a snow-covered landscape. Tardigrades, the microscopic water bears, can survive freezing temperatures by entering cryptobiosis. Tardigrades are among the most resilient creatures ever discovered, tiny animals barely visible to the naked eye that have mastered the art of survival in the harshest conditions imaginable. When faced with freezing, these remarkable creatures enter a state called cryptobiosis, expelling nearly all the water from their bodies and replacing it with protective sugars that prevent ice crystals from damaging their cells. In this dried, dormant state, tardigrades can endure temperatures close to absolute zero, far colder than anything found naturally on Earth. They have survived exposure to the vacuum of space, intense radiation, and pressures that would crush most other life forms. When conditions improve and water returns, they rehydrate and resume their lives as though nothing happened. Scientists study tardigrades to understand the limits of life. They are nature's ultimate survivors. Antarctic fish produce antifreeze proteins that prevent ice crystals from forming in their blood. In the frigid waters surrounding Antarctica, temperatures drop so low that ordinary fish would freeze solid within minutes. Yet several species have evolved a remarkable adaptation, producing proteins that act as natural antifreeze, circulating through their blood and binding to tiny ice crystals before they can grow large enough to cause harm. These antifreeze proteins work differently from the antifreeze we use in cars, not by lowering the freezing point, but by physically attaching to ice and preventing its growth. The fish that carry these proteins swim freely in waters that hover just below the normal freezing point of their tissues, their bodies in a constant delicate balance with the ice around them. This adaptation evolved over millions of years as Antarctica cooled and the surrounding ocean became hostile to life. The fish found a way to survive. Emperor penguins huddle together in temperatures reaching -60 degrees, rotating positions to share warmth. Emperor penguins face the most brutal winter on Earth, breeding on the sea ice of Antarctica during the darkest and coldest months of the year. When temperatures plunge and fierce winds howl across the ice, the penguins gather into enormous huddles, thousands of birds pressing together for warmth in a living mass that moves slowly across the frozen landscape. Those on the outside gradually rotate inward, each bird taking its turn in the sheltered center of the group, where temperatures can be 40 degrees warmer than the exposed edges. This cooperative behavior allows all members of the huddle to survive conditions that would kill an isolated bird within hours. Males balance eggs on their feet throughout the winter, fasting for months while their partners hunt at sea. The huddle is a community of mutual dependence. And from the creatures that endure the cold, we now turn to the physics of how glaciers move and shape the land. Glaciers move in two ways, by sliding over bedrock and by internal flow as ice deforms under pressure. Though glaciers appear motionless to the casual observer, they are in constant, slow motion, flowing under their own immense weight toward lower elevations and the sea. This movement happens in two ways. First, the glacier slides over the bedrock beneath it, lubricated by a thin layer of meltwater created by pressure and friction at the base. Second, the ice itself deforms under the enormous weight of the glacier above, the crystals shifting and flowing like an impossibly slow liquid. The center of a glacier moves faster than the edges, which are held back by friction against the valley walls, and the surface moves faster than the base. This differential movement creates the stresses that open crevasses and shape the flowing ice. A glacier is a river frozen in time, its movement measured not in seconds, but in centuries. Some glaciers surge forward at speeds of tens of meters per day during sudden, dramatic advances. Most glaciers move at a pace measured in centimeters per day, but some periodically experience dramatic surges, racing forward at speeds tens or even hundreds of times faster than normal. During a surge, a glacier that normally moves a few meters per year might advance tens of meters per day, bulldozing everything in its path and dramatically altering the landscape. These surges can last months or years before the glacier returns to its normal slow pace. Scientists believe surges occur when water accumulates beneath the glacier, lifting it slightly off the bedrock and reducing friction, or when internal changes in ice temperature trigger a cascade of rapid movement. Surging glaciers are unpredictable and dangerous, capable of advancing across roads, valleys, and settlements with little warning. The ice awakens and rushes forward. Crevasses form when glacial ice stretches and cracks, creating deep fissures that can be over 30 meters deep. As a glacier flows over uneven terrain or around bends in its valley, the ice is subjected to stresses that cause it to crack and split. These fractures, called crevasses, can open suddenly and without warning, creating deep chasms that may be hidden beneath thin bridges of snow. Crevasses form because ice, while capable of flowing under sustained pressure, is brittle when subjected to rapid stretching. The deepest crevasses can exceed 30 meters, though below that depth the pressure of the overlying ice forces the fractures to close. For mountaineers and polar explorers, crevasses represent one of the greatest dangers of glacial travel, hidden traps that can swallow a person in an instant. Rope teams move carefully across glaciers, probing for hidden voids. The ice conceals its fractures beneath a deceptive blanket of snow. The underside of a glacier can be warmer than the surface, melted by geothermal heat and friction. While the surface of a glacier may be locked in bitter cold, the base can be surprisingly warm, sometimes hovering right at the melting point of ice. This warmth comes from two sources. First, geothermal heat rising from the Earth's interior warms the bedrock beneath the glacier. Second, friction generated by the glacier's movement over rock produces additional heat. Together, these sources can create a thin film of liquid water at the glacier's base, lubricating its movement and enabling it to slide more easily over the terrain below. In some places, entire lakes of liquid water exist beneath kilometers of ice, isolated from the outside world for millions of years. This hidden warmth beneath the frozen surface creates environments that scientists believe may harbor unique forms of life. The glacier keeps its warmest secrets at its foundation. Subglacial rivers flow beneath glaciers, carving tunnels and carrying meltwater to distant outlets. Hidden beneath the ice, rivers of meltwater flow through tunnels carved into the base of glaciers, following paths dictated by pressure gradients and the topography of the bedrock below. These subglacial streams can be substantial, draining vast catchments of melting ice and carrying enormous volumes of water to the glacier's terminus, where they emerge in rushing torrents. The tunnels through which they flow are constantly changing, opening and closing as the glacier shifts, sometimes draining suddenly and catastrophically when new paths open beneath the ice. Scientists studying these hidden waterways use radar and seismic techniques to map the complex network of channels below. The sound of flowing water beneath a glacier is a reminder that even the most solid-looking ice conceals a liquid heart. The rivers beneath the ice never freeze. Glaciers grind the bedrock beneath them, polishing surfaces and leaving distinctive scratches called striations. As a glacier moves over bedrock, it acts like an enormous sheet of sandpaper, carrying embedded rocks and debris that scrape and polish the surface below. The resulting striations are parallel scratches etched into the rock, marking the direction the glacier traveled. In some places, the bedrock is polished as smooth as glass, while in others, deep gouging grooves show where large boulders were dragged beneath the ice. Geologists read these marks like a detailed map, tracing the paths of ancient glaciers long after the ice has melted away. Striations found on mountaintops far from modern ice provide evidence of ice ages past, when glaciers covered regions now green with forests. The scratches remain visible for millions of years, a permanent record of the glacier's slow, patient passage. The rock remembers the touch of ice. And from the movement of glaciers, we now witness the landscapes they carve and leave behind. Fjords are deep, narrow inlets carved by glaciers that retreated and let the sea rush in. Along the coasts of Norway, New Zealand, Chile, and other mountainous shores, the sea reaches inland through deep, narrow channels with sheer walls rising hundreds of meters above the water. These fjords are the flooded valleys of ancient glaciers, carved far below sea level by ice that has long since retreated. When the glaciers melted, the sea rushed in to fill the troughs they left behind, creating some of the most dramatic coastal landscapes on Earth. The depth of many fjords exceeds that of the adjacent ocean, a testament to the erosive power of ice that once filled these valleys to their very rims with frozen rivers. The walls of fjords often display the polished surfaces and striations left by glacial scouring, visible evidence of the forces that shaped them. Fjords are monuments to ice ages past, drowned valleys that remember their creators. U-shaped valleys are the signature of glacial erosion, their smooth walls shaped by ice over millennia. When a glacier fills a river valley and begins to carve its path downhill, it transforms the landscape in ways that remain visible for millions of years. The original V-shaped valley, cut by flowing water, is widened and deeply carved by the glacier, its walls smoothed and steepened by the slowly abrading ice. The result is a U-shaped valley, a broad trough with a flat floor and steep sides that carries the unmistakable signature of glacial sculpting. After the ice retreats, these valleys often hold rivers that seem too small for such enormous spaces, their waters flowing through landscapes carved by forces far more powerful than any stream. Hanging valleys, where tributary glaciers once joined the main ice flow, now end in dramatic waterfalls cascading down the valley walls. These landscapes are the quiet, enduring legacy of ice. Moraines are ridges of debris left behind by glaciers, marking the edges of where ice once stood. As a glacier moves, it carries with it enormous quantities of rock, soil, and debris, scraped from the bedrock below or fallen from the valley walls above. When the glacier eventually melts, this material is deposited in ridges and mounds that trace the former margins of the ice. Lateral moraines mark the edges of the glacier, running parallel to the valley walls. Terminal moraines form at the glacier's farthest advance, curving ridges that show exactly where the ice paused before beginning its long, slow retreat. Geologists read these features like a careful map of the past, using them to reconstruct the size and extent of glaciers that vanished many thousands of years ago. In some places, moraines have dammed valleys to create glacial lakes, while in others they form gently rolling hills across the landscape. Each ridge is a boundary line drawn by ancient ice. Glacial erratics are boulders transported far from their origin by moving ice and left stranded when it melted. Scattered across landscapes once covered by ice, enormous boulders sit perched in places they clearly do not belong. These glacial erratics were plucked from distant mountains, frozen into the base of glaciers, and carried tens or even hundreds of kilometers before being gently deposited when the ice finally melted. By comparing the rock type of an erratic to the bedrock where it now rests, geologists can trace the path the glacier took, following chains of boulders back to their original source. Some erratics are so large and so precariously balanced that they seem to defy gravity, perched upon tiny pedestals of rock. For early humans, these mysterious boulders demanded explanation, often attributed to giants or gods. They are the calling cards of vanished ice, silent evidence of a frozen world that no longer exists. Cirques are bowl-shaped hollows carved into mountainsides where glaciers formed and began their descent. High on mountain slopes around the world, armchair-shaped hollows scoop into the rock, their steep headwalls rising above flat or gently sloping floors. These cirques are the birthplaces of glaciers, the sheltered spots where snow accumulated year after year until it compressed into ice and began to flow downhill. As the glacier grew and moved, it plucked rocks from the headwall and ground away at the floor, carving the distinctive bowl shape that remains long after the ice has melted. Many cirques now hold small lakes called tarns, their waters dark and cold in the shadow of the surrounding cliffs. When glaciers carved from multiple sides of a peak, they left behind sharp ridges called arêtes and dramatic pointed summits called horns. The Matterhorn is perhaps the most famous and dramatic example of such glacial sculpting. Drumlins are teardrop-shaped hills formed beneath glaciers, aligned like schools of fish in the direction of ice flow. Across landscapes once covered by continental ice sheets, elongated hills rise from the plains, their rounded heads pointing upstream and their tapered tails trailing downstream. These drumlins formed beneath the flowing ice, shaped by the movement of the glacier above them. Scientists are still debating exactly how drumlins form, but they are found in vast fields containing thousands of hills, all aligned parallel to the direction of ice flow. From above, a drumlin field looks like a pod of whales swimming in formation, streamlined shapes frozen in the landscape. The sediments within drumlins contain a mix of clay, sand, and boulders, all deposited and shaped by the ice that created them. These gentle hills are among the most intriguing landforms left by the ice ages. Their exact formation remains one of glaciology's enduring mysteries. And from the sculpted landscapes of past glaciers, we now turn to the waters they have stored and released. Glacial lakes form when meltwater collects in basins scoured by ice, their waters often a striking turquoise. As glaciers retreat, they leave behind scooped basins in the bedrock and depressions dammed by moraines, which fill with meltwater to form glacial lakes. These bodies of water can be extraordinarily beautiful, their colors ranging from deep blue to brilliant turquoise, depending on the minerals and sediments suspended within them. Glacial lakes often sit at the foot of retreating glaciers, their surfaces dotted with fragments of ice calved from the glacier's terminus. The water in these lakes is typically cold and clear, fed continuously by the melting ice above. Some glacial lakes are enormous, holding vast volumes of water impounded behind fragile dams of ice or sediment. When these dams fail, catastrophic floods can sweep downstream, reshaping landscapes in hours. These beautiful lakes are transient features of the ice. The color of glacial lakes comes from rock flour, finely ground particles suspended in the water. The striking turquoise and milky blue colors of glacial lakes are not the result of dyes or unusual minerals, but of rock flour, the extremely fine particles of rock ground to powder beneath the moving ice. When meltwater carries this sediment into a lake, the tiny particles remain suspended in the water, scattering and reflecting sunlight in ways that create the distinctive colors. The finest rock flour can remain suspended for years, giving glacial lakes their characteristic opacity and hue. The color changes with the light, appearing deeper blue on overcast days and more brilliant in direct sunlight. Lakes fed directly by glacier melt tend to show the strongest colors, while those further downstream may gradually clear as sediment settles out. The color is a gift from the grinding ice above, a visual signature of glacial activity. Yurkalops are catastrophic floods released when water trapped beneath or within glaciers suddenly bursts free. The Icelandic word jökullaup describes one of nature's most violent phenomena, a sudden outburst flood from a glacier. These floods occur when water that has accumulated beneath or within a glacier, often in subglacial lakes or in basins dammed by ice, suddenly finds a way to escape. The resulting torrent can be immense, releasing volumes of water equivalent to the flow of major rivers in just hours. In Iceland, jökullaups triggered by volcanic eruptions beneath glaciers have devastated coastal plains, sweeping away bridges, roads, and farmland. The floodwaters carry enormous boulders, blocks of ice, and thick loads of sediment, reshaping the landscape through which they pass. These events are difficult to predict and nearly impossible to stop. When a glacier releases its waters, nothing can stand in the way. The Great Lakes of North America were carved by glaciers during the last ice age. The 5 Great Lakes, Superior, Michigan, Huron, Erie, and Ontario, together form the largest system of freshwater lakes on Earth, holding roughly 20% of the world's surface fresh water. These enormous bodies of water owe their existence to the glaciers that advanced and retreated across North America during the last ice age. The weight and movement of the ice sheets scoured the bedrock, carving deep basins that filled with meltwater as the glaciers retreated. The lakes took their current form only about 10,000 years ago, a mere moment in geological time. Today, they support millions of people and a vast ecosystem of fish, birds, and other wildlife. The shores of the Great Lakes still slowly rise, rebounding from the weight of the ice that pressed down upon them for tens of thousands of years. The lakes are the legacy of a frozen past. Many rivers around the world are fed primarily by glacial meltwater, sustaining millions of people. In the great river systems of Asia, South America, and Europe, glaciers serve as frozen reservoirs, storing water as ice during the cold months and releasing it as melt during the warm season. The Ganges, Indus, Yangtze, and countless other rivers depend on glacial meltwater for a significant portion of their flow, particularly during the dry season when other sources are scarce. Hundreds of millions of people rely on these rivers for drinking water, irrigation, and hydroelectric power. As glaciers around the world shrink, the rivers they feed are changing, with some experiencing increased flow in the short term as stored ice melts faster, but facing reduced supply in the decades ahead as the glaciers disappear. The fate of entire civilizations is tied to the health of these frozen water towers. The ice above sustains the valleys below. And from the waters held by ice, we now explore the sounds and silence of frozen places. Glaciers creak, groan, and crack as they move, producing an eerie symphony of ice. A glacier is never truly silent. As the immense mass of ice shifts and flows, it produces a constant chorus of sounds that seem to come from another world. Deep groans emerge from within the ice as billions of tons of frozen water strain against the bedrock below. Sharp cracks ring out across the landscape as new crevasses open in the surface. Low rumbles travel through the ice like distant thunder, the sound of internal deformation as the glacier slowly bends and flows. For those who spend time in glacial landscapes, these sounds become familiar, a background music of the frozen world. Some scientists use microphones embedded in the ice to listen to these sounds, extracting information about the health and movement of the glacier from its voice alone. The ice speaks to those who listen, telling stories of strain and flow, of pressure and release across the frozen expanse. The sound of ice melting underwater creates a distinctive fizzing noise as ancient air bubbles escape. When icebergs or chunks of glacial ice drift into warmer waters and begin to melt, they release air that has been trapped within the ice for thousands of years. As the ice dissolves, these ancient bubbles escape with a distinctive crackling and fizzing sound, sometimes so loud it can be heard from considerable distances. Scientists who lower hydrophones into waters around melting glaciers capture recordings filled with this effervescent chorus, a sound like champagne being endlessly opened. Each bubble carries a sample of ancient atmosphere, air that was trapped when the snow first fell and was compressed into the glacier generations ago. The fizzing of melting ice is the voice of time itself escaping, the release of ancient breaths into the modern ocean. It is a haunting sound that marks the end of a long frozen journey. In polar regions, the silence is so profound that some visitors describe it as deafening. In the vast interior of Antarctica or the frozen reaches of the high Arctic, far from any machinery or wildlife, visitors encounter a silence more complete than almost anywhere else on Earth. Without wind, there are no sounds at all, no rustling leaves, no gently flowing water, no birdsong to fill the air. The quietness is so absolute that some people find it disorienting, an absence of sound so total that it seems to press against the ears. In this profound silence, the slightest movement becomes audible, the crunch of a footstep on snow, the whisper of fabric rubbing against fabric. Some visitors report hearing their own heartbeat, their own blood flowing softly through their veins. The silence of the polar regions is not empty at all. It is a profound presence, a vast and encompassing stillness that envelops everything within it. Wind sculpts snow into delicate formations called sastrugi, ridges aligned with the prevailing breeze. Across the windswept plains of Antarctica and the frozen Arctic tundra, the snow surface is carved into an endless array of ridges, grooves, and delicate wave-like patterns. These formations, called sastrugi, are sculpted by the persistent winds that sweep across the ice, eroding soft snow from one side and depositing it on the other. The ridges align with the direction of the prevailing wind, creating parallel rows that can stretch for kilometers across the landscape. For explorers traveling across polar regions, sastrugi can make progress exhausting, the hard frozen ridges catching at skis and sledges with every step. Yet they are also strangely beautiful, the snow carved into shapes that resemble frozen ocean waves or rippled sand dunes. The wind writes its flowing signature upon the snow, a lasting record of its passage. Frost flowers form on new sea ice, delicate ice crystals that bloom like frozen blossoms. In the coldest polar conditions, when the temperature difference between the relatively warm ocean water and the frigid air above is greatest, delicate structures of ice crystals grow on the surface of newly formed sea ice. These frost flowers are exquisitely beautiful, clusters of ice needles and branching crystals that resemble miniature bouquets of frozen flowers. They form when water vapor sublimes from the warmer ice below and refreezes on any small irregularity in the surface, building up into fragile structures just a few centimeters tall. Frost flowers exist only briefly, lasting hours or days before wind or further snowfall destroys them. They are among the most delicate and ephemeral phenomena in all of nature, fleeting works of art created by the cold itself. Scientists also study them for their role in atmospheric chemistry. And as you rest with these frozen wonders, let your thoughts drift like snowflakes on a windless night. There is nothing to solve, nothing to understand. Simply let the stillness deepen and feel your body becoming heavy and peaceful. Diamond dust is a phenomenon where ice crystals suspended in the air create a sparkling, dreamlike haze. On the clearest, coldest polar days, when the sky is cloudless and the temperature plunges to extreme lows, tiny ice crystals form directly in the air itself, floating suspended in the atmosphere and catching the light like countless miniature diamonds. This phenomenon, called diamond dust, creates a magical shimmering effect, as though the very air has turned to glitter. The crystals are so small and light that they drift almost motionless, sparkling whenever sunlight strikes them at the right angle. Diamond dust can create stunning optical phenomena, including sun dogs, halos, and pillars of light that seem to stretch from the sun toward the horizon. Standing within a fall of diamond dust feels like being inside a snow globe, surrounded by gently twinkling points of light. It is one of nature's most enchanting spectacles. And from the beauty of ice and frost, we now turn to how frozen places have shaped human history. Ice ages forced early humans to adapt, migrate, and develop technologies to survive the cold. The ice ages that have periodically gripped the Earth were crucibles of human evolution, forcing our ancestors to adapt or perish in the face of advancing ice and plummeting temperatures. As glaciers spread across the northern continents, human populations were pushed southward, crowded into refugia where conditions remained tolerable. Those who survived developed new technologies, stitched clothing from animal skins, built shelters against the cold, and mastered fire to warm themselves and cook their food. The challenges of the Ice Ages may have spurred the development of language, cooperation, and the cognitive abilities that set humans apart from other species. When the ice finally retreated, human populations expanded rapidly, carrying the innovations born of necessity into every corner of the newly habitable world. The cold shaped who we are. The Bering Land Bridge, exposed during ice ages, allowed humans to walk from Asia to North America. During the last ice age, so much of the world's water was locked up in glaciers that global sea levels dropped by more than 100 meters, exposing vast areas of seabed that are now submerged beneath the rising waves. One of the most significant of these exposed areas was Beringia, a large land bridge connecting Siberia to Alaska across what is now the Bering Strait. For many thousands of years, this bridge of tundra and grassland provided a pathway for animals and eventually humans to cross between the continents. The first Americans walked across this land bridge, following the herds of mammoths and other large animals that grazed on the steppe. When the Ice Age ended and the seas rose once more, the land bridge disappeared beneath the waves, severing the connection between the continents. The descendants of those first crossers would populate 2 entire continents. Frozen passes in the Alps have yielded preserved remains of ancient travelers, including Ötzi the Iceman. The high mountain passes of the Alps have been trade routes and migration corridors for thousands of years, and the glaciers and snowfields that guard these passes have occasionally claimed the lives of those who crossed them. When travelers fell into crevasses or were overcome by storms, their bodies were sometimes preserved by the cold, frozen into the ice, and hidden from the world for centuries or even millennia. As glaciers have retreated in recent decades, these ancient remains have begun to emerge, offering remarkable windows into the past. Clothing, tools, and even the bodies themselves can be preserved in extraordinary detail, providing valuable evidence of how people lived, what they ate, and how they died. Each discovery is both a tragedy and a gift, a life lost to the cold and a story preserved by the ice. Ötzi the Iceman was preserved in glacial ice for over 5,000 years before being discovered. In 1991, hikers in the Ötztal Alps on the border between Austria and Italy stumbled upon a body emerging from a retreating glacier. What they had found was the oldest known natural human mummy in Europe, a man who had died approximately 5,300 years ago during the Copper Age. Ötzi, as he came to be called, was remarkably well preserved, his skin, clothing, tools, and even his last meal still intact after millennia in the ice. Scientists have analyzed every aspect of his remains, learning about his health, his diet, his genetic ancestry, and the violent end that befell him, a flint arrowhead lodged in his shoulder. Ötzi offers a direct connection to a distant past, a single individual whose life and death can be studied in remarkable detail. The ice preserved his story with extraordinary fidelity. The Little Ice Age, lasting from the 14th to the 19th century, brought cold winters to Europe and beyond. Between roughly 1300 and 1850, the Northern Hemisphere experienced a period of cooling known as the Little Ice Age, when average temperatures dropped by 1 or 2 degrees and the effects rippled through society. Glaciers advanced down alpine valleys, swallowing villages that had stood for generations. Harsh winters brought famine and disease, reshaping economies and triggering social upheaval. The causes were likely a combination of reduced solar activity, increased volcanic eruptions, and changes in ocean circulation patterns. Artists of the period captured the frozen landscapes in their paintings, showing scenes of ice skating and winter fairs that would be impossible in the same locations today. The Little Ice Age serves as a reminder that even modest changes in climate can have profound effects. Rivers and canals that rarely freeze today were once thick enough to hold winter fairs during the Little Ice Age. During the coldest winters of the Little Ice Age, rivers and canals that now remain liquid throughout the year froze solid for weeks or months at a time. The Thames in London, the canals of the Netherlands, and waterways across Europe became venues for frost fairs, impromptu markets and festivals held on the ice. Vendors set up stalls, entertainers performed, and entire communities gathered to celebrate the frozen waterways. These events are well documented in paintings, sketches, and written records from the period, providing a vivid picture of how cold those winters truly were. The last Great Frost Fair on the Thames was held in 1814. Since then, warmer temperatures and significant changes to the river's flow have prevented such freezes from occurring. The frozen fairs exist now only in memory and art. And from the influence of ice on human history, we now explore the explorers who ventured into frozen wildernesses. The race to reach the South Pole captured the imagination of the early 20th century. In the first decades of the 20th century, reaching the South Pole became a symbol of national prestige and human achievement, drawing expeditions from Britain, Norway, and other nations. The most famous race pitted Roald Amundsen of Norway against Robert Falcon Scott of Britain in a contest that would end in tragedy. Amundsen reached the pole first on the 14th of December, 1911, using dog sleds and careful planning honed over years of Arctic experience. Scott arrived a month later, only to find the Norwegian flag already flying. His entire polar party perished on the return journey, overcome by cold, hunger, and exhaustion. Their bodies and diaries were found the following spring. The stories of both expeditions have become enduring legends of exploration, tales of triumph and tragedy in the harshest place on Earth. Ernest Shackleton's Endurance expedition became legendary for survival after their ship was crushed by ice. In 1914, Ernest Shackleton set out to cross Antarctica on foot, but his ship, the Endurance, became trapped in the pack ice of the Weddell Sea before ever reaching the continent. For many long months, the crew watched helplessly as the ice slowly crushed their vessel, until it finally sank beneath the frozen sea. Stranded on drifting ice floes, Shackleton led his men in a desperate bid for survival that would last nearly 2 years. They eventually reached Elephant Island by lifeboat, from where Shackleton sailed 800 miles in a small boat across the stormiest ocean on Earth to fetch help. Miraculously, all 27 men survived. Shackleton's leadership in the face of disaster has become a model studied by leaders in every field around the world. His remarkable story endures as a testament to human resilience. The Northwest Passage, long sought as a shortcut between oceans, was blocked by Arctic ice for centuries. For hundreds of years, European explorers sought a navigable route through the Arctic archipelago of Canada, hoping to find a shortcut between the Atlantic and Pacific Oceans. The Northwest Passage, as it came to be known, claimed the lives of countless sailors who found their ships trapped in ice that never released them. The most famous victim was Sir John Franklin's ill-fated expedition of 1845, which vanished entirely with all 129 men aboard. The passage was finally navigated by the determined Roald Amundsen between 1903 and 1906, though it remained largely impractical for commercial shipping. Now, as Arctic ice retreats in the warming climate, the passage is becoming more accessible. The route once blocked by ice may soon become a major shipping lane. Fridtjof Nansen deliberately froze his ship into Arctic ice to drift across the polar sea. In 1893, the Norwegian explorer Fridtjof Nansen embarked on one of the most audacious expeditions in polar history. Rather than fighting against the ice, he designed a ship called the Fram with a specially rounded hull that would rise up when squeezed by pressure, and deliberately sailed it into the pack ice north of Siberia. His plan was to let the natural drift of the ice carry the ship across the Arctic Ocean toward the North Pole. For 3 years, the Fram drifted slowly with the ice, while Nansen conducted scientific observations and eventually set off on foot toward the pole itself. He reached a latitude farther north than any human before him. The expedition proved his theory of polar drift and returned safely with invaluable scientific data. Nansen's innovative thinking transformed polar exploration forever. And from the explorers of frozen frontiers, we now turn to the creatures that have long called these icy realms home. Narwhals, the unicorns of the sea, live year-round in Arctic waters, navigating through shifting ice. In the frigid waters of the Arctic, among the ice floes and frozen channels, lives one of the most mysterious whales on Earth. The narwhal, with its spiraling tusk that can grow up to 3 meters long, has inspired legends of unicorns and other magical creatures since the Middle Ages. These remarkable tusks are actually elongated teeth, found primarily in males, and are used in social displays and possibly for sensing subtle changes in the surrounding environment. Narwhals spend their entire long lives in the Arctic, diving to great depths to feed on fish and squid beneath the ice. They navigate through leads and cracks in the ice, sometimes becoming trapped when the ice shifts unexpectedly. Their ability to survive in one of the harshest marine environments on Earth makes them remarkable creatures. They are icons of the frozen sea. Walruses use sea ice as resting platforms between dives into the frigid ocean depths. The walrus is one of the Arctic's most iconic and truly impressive animals, a massive pinnipede with long tusks, whiskered snout, and thick insulating blubber that protects it from the brutal cold. Walruses depend on sea ice as essential platforms where they can rest between foraging dives, haul out to nurse their young, and escape from predators such as polar bears and orcas. They use their sensitive whiskers to detect clams and other shellfish hidden on the seafloor, then suck the meat from the shells with extraordinary efficiency. As Arctic sea ice diminishes in the warming climate, walruses are forced to crowd onto shrinking ice floes or haul out on land, where they are far more vulnerable and where crowding can lead to deadly stampedes. The fate of the walrus is tied directly to the health of the Arctic sea ice. They are creatures entirely shaped by the frozen sea. Arctic foxes grow white winter coats so effective that they remain warm at -70 degrees. The Arctic fox is a small but remarkably resilient creature, superbly adapted to survive the brutal cold of the far north. In winter, its thick coat transforms from gray or brown to brilliant white, providing both camouflage against the snow and exceptional insulation. This fur is among the warmest of any mammal on Earth, allowing the fox to remain active in temperatures that would kill most other animals within minutes. Arctic foxes do not begin to shiver until temperatures drop below -70 degrees, a remarkable testament to the effectiveness of their adaptations. They hunt lemmings and other small prey, often caching food for the lean months when hunting becomes difficult. In years when prey is scarce, Arctic foxes will travel enormous distances across the snow in search of food. They are survivors of the harshest winter. Snowy owls hunt silently across tundra landscapes, their white plumage blending with the snow. The snowy owl is a bird of the Arctic tundra, a large and powerful predator perfectly adapted to hunting in the land of endless winter. Its white plumage provides camouflage against the snow and ice, while its keen eyesight allows it to spot prey even in low light. Unlike most owls, snowy owls are often active during the day, taking advantage of the continuous daylight of the Arctic summer to hunt. Their primary prey are lemmings, and in years when lemming populations peak, snowy owls raise large broods of chicks to take advantage of the abundance. When prey becomes scarce in the north, snowy owls sometimes migrate far southward, appearing in surprising and unexpected places. These seasonal eruptions bring the spirit of the Arctic into more temperate lands. The snowy owl carries the profound silence of the tundra wherever it flies. Adelie penguins navigate hundreds of kilometers across Antarctic ice to reach their breeding colonies. Each year, Adelie penguins undertake remarkable journeys across the frozen landscape of Antarctica to reach the rocky shores where they breed. These small but determined birds march for hundreds of kilometers over sea ice and snow, following routes that may have been used by their ancestors for thousands of years. When they arrive at their colonies, they build nests of small stones, jealously guarding each pebble and sometimes stealing from neighbors. Both parents take turns incubating the eggs and feeding the chicks once they hatch. The timing of their breeding is crucial, dependent on the sea ice breaking up early enough to allow access to the open water, where they hunt for krill and small fish. As the patterns of Antarctic ice change, the Adelie penguins are adapting, shifting their colonies and routes. Their journeys across the ice are ancient rituals. Krill form the foundation of the Antarctic food web, thriving beneath the sea ice. In the cold waters surrounding Antarctica, vast swarms of tiny crustaceans called krill form the base of a food web that supports whales, seals, penguins, and countless other species. These small animals, each only a few centimeters long, gather in concentrations so dense they can be seen from space, turning the ocean pink with their sheer numbers. Krill depend on the algae that grow on the underside of sea ice, grazing on the frozen ceiling of their world. Without this sea ice habitat, krill populations decline, and the effects ripple through the entire Antarctic ecosystem. Scientists estimate that there are hundreds of millions of tons of krill in the Southern Ocean, making them one of the most abundant and ecologically important animal species on Earth. Their tiny bodies sustain giants. The entire Antarctic ecosystem rests upon their quiet existence. And from the creatures of ice, we now turn to the surprising discoveries hidden within frozen places. Scientists have revived ancient microbes frozen in permafrost for tens of thousands of years. In laboratories around the world, scientists have coaxed life from samples of permafrost that have been frozen for tens of thousands of years. When carefully thawed under sterile conditions, some of the ancient bacteria and other microorganisms within these samples have revived, resuming metabolic activity after millennia of frozen dormancy. These experiments reveal the remarkable resilience of life, its ability to persist in states of suspended animation that stretch human comprehension. The revived microbes offer glimpses into ancient ecosystems and evolutionary pathways, living fossils that can be studied in ways that ordinary fossils cannot. Yet these experiments also raise questions about what else might be preserved in the frozen north and what might awaken as the permafrost thaws. The ancient sleepers are beginning to stir. Seeds preserved in frozen soil have been germinated after lying dormant for over 30,000 years. In Siberia, scientists have recovered seeds from ancient squirrel burrows preserved in the permafrost, frozen in place for more than 30,000 years. When carefully germinated under laboratory conditions, some of these seeds have sprouted, producing plants identical to species that still grow in Siberia today. The discovery demonstrates the extraordinary preservation possible in frozen ground, where seeds can remain viable for periods that stretch back to the last ice age. These experiments blur the line between past and present, bringing ancient organisms back to life in a world utterly different from the one in which they were buried. The plants that grow from these seeds are time travelers, genetic messages from the distant past. They prove that life can wait, patient and dormant, across unimaginable spans of time. Ancient viruses have been discovered in melting permafrost, some still capable of infecting modern hosts. As permafrost thaws across the Arctic, it is releasing material that has been locked in ice for thousands of years, including ancient viruses that retain their ability to infect. Scientists have recovered remarkably giant viruses from Siberian permafrost that, when exposed to their ancient hosts, proved still capable of infection after 30,000 years of dormancy. This discovery raises questions about what other pathogens might emerge from the melting ice, including some that might pose risks to modern organisms. The prospect is not one of imminent danger, as most ancient viruses cannot infect humans, but it is a sobering reminder that the permafrost is more than frozen soil. It is a biological archive that is now being opened without our consent. The thawing ground releases its secrets, both wondrous and unsettling. A perfectly preserved cave lion cub was found in Siberian permafrost, frozen for over 40,000 years. In the frozen ground of Siberia, miners and researchers have made remarkable discoveries, including the perfectly preserved bodies of Ice Age animals that died and were frozen before they could decay. Among the most stunning of these finds is a cave lion cub, a species that went extinct thousands of years ago, found frozen in such pristine condition that its fur, whiskers, and even its facial expression remain intact. The cub likely died in a sudden cave collapse and was frozen almost immediately afterward, preserving it through the tens of thousands of years that followed. Scientists have been able to carefully study its anatomy, its genetics, and even hope one day to clone such remarkable creatures back to life. The ice keeps its dead forever young. These frozen remains offer extraordinary glimpses of lost worlds. Frozen peat bogs have yielded intact human remains, their features remarkably preserved by the cold. In the frozen wetlands of northern Europe and elsewhere, peat bogs have preserved human remains in extraordinary condition, their skin, hair, and facial features intact after thousands of years. These bog bodies, as they are known, offer intimate glimpses into the lives and deaths of ancient peoples, revealing details about their diet, health, clothing, and often the violence that ended their lives. The combined effect of cold temperatures, acidic water, and low oxygen creates conditions that inhibit decay, turning flesh to leather and preserving bodies that would otherwise have vanished millennia ago. Scientists have carefully studied these remains to learn about ancient societies, their mysterious rituals of sacrifice and execution. Each body is a mystery and a tragedy. The bogs keep their dead in perpetual silent repose. And from the discoveries within ice, we now turn to the changing nature of Earth's frozen places. The vast majority of the world's glaciers are retreating, losing more ice each year than they gain. Across the planet, from the high peaks of the Alps to the mountains of South America, from the ice caps of Norway to the glaciers of the Himalayas, frozen rivers of ice that have existed for thousands of years are shrinking. The vast majority of the world's glaciers are now losing more mass each year than they gain through snowfall, a troubling trend that has accelerated markedly in recent decades. Photographs taken a century apart show glaciers that once filled entire valleys now reduced to thin ribbons of ice clinging to the highest ground. The meltwater flows into rivers and oceans, contributing to rising sea levels and fundamentally changing the hydrology of entire regions. Scientists monitor these alarming changes with satellite imagery and field measurements. The retreat of the glaciers is written across the mountains. Some glaciers that have existed for thousands of years may disappear entirely within this century. For many glaciers around the world, particularly smaller ones at lower elevations and equatorial latitudes, the future is one of complete disappearance. Scientists project that entire glacial systems that have existed since the last ice age or longer will melt away within the coming decades, leaving behind only bare rock and memories of ice. Mountain communities that have lived alongside these glaciers for generations will watch them vanish, along with the reliable water supplies and cultural identity they have provided. In some places, communities are holding funeral ceremonies for dying glaciers, marking their loss with ritual and remembrance. The disappearance of these ice bodies is not merely a geographical change. It is a transformation of landscapes, ecosystems, and human relationships with the frozen world. Some glaciers are already beyond saving. The Antarctic ice sheet is losing mass at an accelerating rate, contributing to rising seas. The Antarctic ice sheet contains enough frozen water to raise global sea levels by more than 50 meters if it were to melt entirely, a scenario that is fortunately not expected for many millennia. Yet even small changes to this vast reservoir of ice have significant implications for coastal communities around the world. In recent decades, the rate at which Antarctica is losing ice has increased dramatically, particularly in West Antarctica, where warming ocean waters are undermining the glaciers from below. The ice that flows into the sea through these glaciers determines how quickly sea levels rise. Scientists are watching carefully, measuring the movement of every major glacier with satellites and sensors. The future of coastal cities depends in part on the stability of ice thousands of kilometers away. Antarctica's frozen heart affects every shore. And as these truths settle gently within you, let them simply rest, like snow falling on still water. There is no urgency, no need for answers. Let your body sink deeper into comfort and allow the quietness to surround you. Thawing permafrost is causing the ground to collapse in parts of Siberia and Alaska. Across the Arctic, ground that has been frozen for thousands of years is beginning to thaw, and as it does, the landscape is collapsing. The ice that once held soil and rock together is melting away, leaving behind sinkholes, landslides, and surreal features of buckled and sunken terrain. Buildings that once stood on solid ground are now tilting and cracking as their foundations shift. Roads and runways are becoming unusable as the ground beneath them heaves and settles. In Siberia, enormous craters have opened in the tundra, some hundreds of meters across, formed as underground ice melts and the surface gives way. These changes are not gradual. They can happen suddenly and catastrophically, transforming stable landscapes overnight. The permafrost that seemed permanent is proving anything but. The ground itself is beginning to dissolve. Glacial meltwater is altering ocean currents, which in turn affects weather patterns around the world. The great ocean currents that circulate heat around the planet are driven in part by differences in water temperature and salinity. As glaciers melt, enormous volumes of fresh water pour into the oceans, diluting the salty seawater and potentially disrupting the patterns of circulation that have existed for millennia. Scientists are watching particularly closely the currents of the North Atlantic, where cold, dense, salty water sinks to power a global conveyor belt of ocean movement. If this delicate circulation slows or fails, the effects on weather patterns could be remarkably dramatic and far-reaching, potentially cooling parts of Europe even as the rest of the world warms. The connections between ice and ocean are remarkably complex and deeply intertwined. What melts in Greenland may bring storms to distant shores. Ice shelves act as buttresses holding back glaciers, and their collapse accelerates ice loss from the land. Around the edges of Antarctica and Greenland, floating platforms of ice called ice shelves extend out over the ocean, attached to the glaciers that flow from the interior. These shelves act as natural barriers, slowing the flow of ice from the land into the sea. When an ice shelf collapses, as has happened dramatically in several parts of Antarctica in recent decades, the glaciers behind it accelerate, pouring ice into the ocean at rates far faster than before. The loss of these buttressing shelves is one of the reasons Antarctica's contribution to sea level rise has increased so dramatically in recent years. Scientists are monitoring the remaining ice shelves carefully, watching for signs of warming waters eating away at them from below. The collapse of a major ice shelf can change the future of coastlines worldwide. And from the changes unfolding in frozen places, we now return to the quiet wonder of ice itself. Every snowflake that falls begins as a tiny crystal forming around a speck of dust or pollen. High in the atmosphere, where the air is cold enough for water vapor to freeze, every snowflake begins its life around a tiny nucleus, a speck of dust, a grain of pollen, a fragment of volcanic ash drifting gently on the wind. Water molecules attach to this nucleus and begin to arrange themselves into the hexagonal structure that is the fundamental geometry of ice. As the crystal falls through the atmosphere, it passes through different zones of temperature and humidity, and each change in conditions causes the crystal to grow in different ways. Branches extend and split, facets form and flatten, creating a structure that records the entire journey from cloud to ground. By the time a snowflake lands gently upon the earth, it has become a unique and delicate work of art. No human hand could ever craft such intricate perfection. No two snowflakes are ever exactly alike, each one a unique record of its journey through the atmosphere. The saying that no two snowflakes are alike is not merely poetry. It is remarkable scientific truth. Each snowflake follows its own unique path through the atmosphere, encountering its own sequence of temperatures and humidities, tumbling and spinning in ways that no other crystal will ever precisely replicate. Even snowflakes that form in the same cloud and fall side by side will grow slightly different branches, develop slightly different symmetries, and arrive on the ground as distinct individuals. The complexity of these tiny crystals is staggering, with trillions of water molecules arranged in patterns that will never be repeated. Scientists who study snowflakes under microscopes find endless variation and endless beauty within each one. Each frozen flake is a memoir of a journey that began in the clouds above. Fresh snow is mostly air, and its soft silence comes from the way it absorbs sound waves. A blanket of fresh snow is remarkably light, made up of delicate ice crystals with air filling most of the space between them. This porous structure gives fresh snow its characteristic softness and another remarkable property: its ability to absorb sound waves that travel through the quiet air. Sound waves that would normally bounce off hard surfaces are instead absorbed by the snow, muffled and scattered by the countless tiny air pockets within the soft snowpack. This is why the world seems to fall silent after a fresh snowfall, why even busy streets become strangely quiet and sounds seem to come from far away. The snow creates a hush that settles over the landscape, a natural soundproofing that transforms the familiar into something deeply peaceful. This gentle silence is one of winter's most calming and beautiful gifts to us all. Ice has over 18 known crystalline structures, though only one forms naturally on Earth's surface. The ice we encounter in our daily lives, the ice in glaciers and snowflakes and frozen ponds, is just one of many possible forms that frozen water can take. Scientists have discovered over 18 distinct crystalline structures of ice, each forming under different conditions of temperature and pressure. Most of these exotic forms exist only in laboratories, under extreme pressures that mimic the conditions found deep within ice moons of the outer solar system. The ice that forms naturally on Earth's surface is called Ice 1H, a hexagonal crystal structure that gives snowflakes their six-fold symmetry and allows ice to expand as it freezes. This remarkable property is crucial for life on Earth, allowing ice to float on water and insulating lakes and oceans from the worst of winter's cold. Our familiar ice is just one chapter. The aurora borealis dances most vividly above frozen lands, where clear skies meet long polar nights. In the skies above the Arctic, curtains of green, purple, and red light ripple and dance across the darkness, one of the most beautiful natural phenomena on Earth. The aurora borealis, or northern lights, occurs when charged particles from the sun stream into Earth's atmosphere and collide with gases, causing them to glow with beautiful ethereal light. This display is most vivid over frozen lands, not because of the ice itself, but because the long polar nights provide darkness in which to see the lights, and the cold, dry air offers exceptional clarity. Indigenous peoples of the Arctic have long told stories about the aurora, seeing in its shifting patterns the spirits of ancestors, the souls of the departed, or omens of events to come. The lights are silent witnesses to the frozen world below. They dance for all who watch. Ice reflects sunlight back into space, helping to regulate the temperature of the entire planet. The bright white surfaces of ice and snow are among the most reflective natural surfaces on Earth, bouncing back into space much of the sunlight that strikes them. This reflectivity, called albedo, plays a crucial role in regulating Earth's temperature, keeping the polar regions cold and helping to balance the energy budget of the entire planet. When ice melts and dark ocean or land is exposed beneath it, more sunlight is absorbed rather than reflected, leading to additional warming that melts more ice in a self-reinforcing cycle. This powerful feedback mechanism is one of the reasons why polar regions are warming faster than the rest of the planet. The ice that protects us is itself protected by remaining frozen, its brilliant surface shielding the Earth from the full force of the sun and helping to keep our world in balance. In the stillness of frozen places, time itself seems to slow, preserving the breath of the ancient Earth. There is a quality to frozen landscapes that feels timeless, a sense that in these vast white spaces, the ordinary rush of existence pauses and something deeper quietly emerges. The ice preserves not only physical remnants of the past, but also a quality of stillness that is increasingly rare in our busy and noisy modern world. To stand on a glacier or upon the frozen sea, surrounded by silence and space, is to experience something ancient and deeply profound. The breath of fresh air you inhale may have been exhaled by the Earth itself, released from ice that formed when the world was young. In these frozen places, the boundaries between past and present blur, and the planet reveals its longer rhythms. The ice invites us to slow down, to listen, and to remember. And there, in the quiet, the ancient Earth breathes still. And now the frozen wonders of Earth begin to fade gently into the hush of the night. We have wandered through places where time moves slowly, where ice holds the memory of ancient atmospheres and glaciers carve their patient paths across the land. From the white silence of Antarctica to the permafrost plains of Siberia, from ice cores that read like history books to creatures that thrive in the heart of winter, we have touched a world most will never see, a world that shapes our planet more than we often realize. These frozen places, vast and quiet, continue their slow work even as you rest. If this journey brought you peace tonight, consider subscribing or sharing this video with someone who might also need a quiet place to rest. There are more wonders waiting, more calm nights ahead, and we would love to have you return. Right now, as you lie here, the lessons of ice linger gently around you. Somewhere, a glacier is creaking forward in the darkness, a snowflake is forming high in the atmosphere, and permafrost is holding fast to secrets from a world before humans walked the Earth. You carry within you the same water that has cycled through ice ages and oceans, through glaciers and clouds, connecting you to the frozen world in ways you may never fully know. Let your eyelids grow heavy, and if they wish to close, let them. Take one slow breath in, feeling the cool air settle in your lungs like mist on a mountain, and then release it long and easy. Let your body become still, like a frozen lake under a winter sky. There is nowhere you need to be. The ice will wait for you. Tonight, as you rest, the frozen places of Earth continue their quiet existence. Glaciers inch forward through valleys, ice cores lie in silent vaults preserving ancient air, and snow falls somewhere on a distant peak, beginning its long journey toward the sea. Somewhere, a polar bear drifts on sea ice beneath the stars, and auroras shimmer above landscapes where no human voice disturbs the stillness. You are a small, warm presence within this vast frozen world, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that even the vastest ice sheets began as single snowflakes, gathering one by one, patient and unhurried, into something magnificent beyond measure. This has been Drowsy Discovery. Good night.